Alright, so let's talk about the definition of work. So definition, I might have sent these notes to you already, but I'm going to write it out just in case, and I'll send it to you again. The definition of work done by a constant force. So keyword is constant. Okay, so if an object is moved a distance in the direction of an applied constant force, which we'll call F, then the work W done by the force is defined as the following: force times distance. So F times D. So if it's constant, super easy. You just multiply the two numbers and you're done. Okay. So that's usually what you do at the beginning of physics, like physics 1, maybe. Yeah, it should be physics 1. Because of force, they're usually they have those questions like they're pushing a block or they're pushing a car up a hill or something. But those forces are usually constant, meaning you have 2 newtons of force in one direction, and then you have 3 units of force a different direction. But calculus comes in when the force is a function, meaning it's a variable force. So this first example, no big deal, right? So let's go ahead and do that. This is kind of similar to like the beginning of the work chapter in physics 1, right? So determine the work done. In lifting a 50-pound object 4 feet. So all you have to do is multiply the force and distance, and that's it. So the work done would be the 50 pounds times feet, 4 feet. So I'm pushing this object or lifting it up. I'm picking up a box or whatever, right? The work done would simply be 50 times 4, which is approximately, actually equal to 200 foot-pounds. And in physics, usually we use newtons, or if we use the other system, use foot-pounds. This would also be equivalent to 200 joules. Okay, so those types of examples, you have a couple of these in the homework. The first few will be something like this, but then right away we'll start talking about variable force. So let's go ahead and move on to variable. So the definition of work done by a variable force So here we go. So if an object is moved along a straight line by a continuous I spelled that wrong. It should be U-O-U-S. Continuously varying force, which we will call capital F of X. Then the work done by the force, one second, sorry. As the object is moved from x equals A to x equals B. So the work will be given, or is given by, the following formula. So from A to B integral, work will be equal to this in the integral of the force function, the variable force, times dx. Okay. So we're gonna have to integrate to find the work in these these next few problems. All right. The integrals won't be crazy; it'll be like basic integrals, but everything all the integral techniques we've learned so far are fair game. But let's go over Hooke's law. We'll probably need this. There's a couple of spring questions on the homework. So Hooke's law. So for constant spring, F is equal to KD. Or you could say that the F of X function, forcing function, is equal to KX. Instead of just F, we'll call it F of X. Okay. Where D or X is the distance a spring is compressed or stretched. From its original length. Okay, so that's what X is, the F of X. Okay, and K is the constant no, dyslexic today. There we go. Constant of proportionality. They also call it the spring constant in physics. But in math, these types of constants in general are just called the proportional constant. So I'll just in parentheses here. Also known as the spring constant. Which depends on the nature of the spring. So depending on what kind of spring you have different constants or spring constants. Okay. Okay, so let's go ahead and try an example that uses variable force on a spring. Okay. So a force of 30 pounds compresses a spring 3.6 inches from its natural length of 18 inches. Find the work done in compressing the spring. All right, so part A. So part A, we'll say that, yeah, we'll do what it says. It's a total compression of 3.6. All right, so what are the unknowns, right? So what is known? Said a force of 30 pounds. So we do have F technically. We don't know K, the spring constant. D, what is the distance? Ouch. Even 6 feet. So currently we have, let's make sure here we got everything correctly. So they said inches, right? 30 is pounds. So we would say that would be technically foot pounds, right? So if we use our Hooke's law here, F equal to K times distance, to have it all in the same units, we'd have to convert this to feet. You see what I mean? Then go ahead and plug in the 30 feet, foot pounds. We can plug in the distance, but it needs to be changed. So technically it is 3.6 inches. But if I want that in feet, right? So I want everything in the same units. Um, this would be K times 3.6 over 12 feet, right? Technically. Let me grab my calculator because we got decimals going on. So we solve for K. I'm going to go ahead and solve for K here, multiplying by 12 both sides. That'll give us 360 equal to K times 3.6. So K would be 360 over 3.6, approximately south, still equal. But once we divide it, it will be approximate. Well, actually, no, it's actually still exact. Cool. So we got our spring constant, 100. And since we're going to be using the same spring for part A and part B, K should not change. So K, the constant of proportionality, or the spring constant, is 100. So now that we have it, we have to figure out what is the compression, right? What is the distance, right? Because to find the work, you need to integrate over some distance. So right now we have the integral of the constant times your x dx, right? Since we have the k, we should be able to integrate this no problem. The question becomes, though, how much compression was done. So the original length was 18 inches, right? So it might help to draw this a little bit. I'll try to draw it over here. Let's say right here, the total, right? They said is 18 inches. In part A, they're going to compress it 3.6. So if I compress the spring 3.6, that length would be what? What's left over? Let's see here. No, we should have 14.4, but either way, the formula said the distance on the, or the bounds on the integral is just how far it was compressed. So it'd be from some zero distance compressed all the way to 3.6. So it'd be 0 to 3.6, but we got to leave it in terms of feet, right? Because we're going to get foot pounds for the work. Okay. So make sure you put 3.6 over 12 there. So the integral is no big deal, right? That's going to be 50x squared from 0 to 3.6 over 12 feet, which will be 50 times whatever this number is squared minus 0. So what the hell is that? Let's see. Looks like 4.5 foot-pounds. Or joules. Part B says compressed an additional, crap, can't spell today. An additional 3.6. One moment. Okay. So additional 3.6 inches. So that means that I'm going to go another 3.6. So the total would be 7.2, right? So we're going to integrate from, so they're compressing it a little bit more, right? So we're starting here and we're compressing further. So the integral would be 3.6 over 12 all the way until 7.2 over 12. Same spring constant, so that doesn't change. So then you'll get your same integral, right? Nothing's different. This will be 50 x squared from 3.6 over 12, 7.2 over 12, which is 50 times 7.2 over 12 squared. I'm going to factor the 50 out just to save space. 3.6 over 12 squared. Anyway, at the end you'll get like some decimal, about 13.5 foot-pounds, or joules. Is there any questions on part A or part B? Does the idea make sense? Do you see why we need an integral instead of just a basic work times distance, or force times distance? Okay. All right, we'll move on to 7.6 then. This will be the last section for chapter 7. I'm not gonna do what's it called? Fluids. Fluid. I forgot what it was called. Pressure, I think it was. 7.7. We're not doing 7.7. Moments, center of mass, and centroids. Okay, some basic ideas here. I'm assuming you've all had some sort of physics, so it won't hit you too hard on that. So we know that force is equal to mass times acceleration, right? Or ma. A moment is equal to m times x. X is the length of the moment arm, and m is the mass of whatever. So in this example, we're going to do actually, yeah, that's fine. 1 second. Yeah, m is still mass here. X is the length of the whatever moment arm we're talking about. Okay, so all right. So moment about the origin, which we'll call m0, is found by summing all these pieces here. So m sub 0 is equal to the sum of m1 x1 plus m2 x2 all the way till mn xn. All right. If m0 is equal to 0, then the system is said to be in a state of equilibrium. Now, for a system that is not in equilibrium, the center of mass is defined as the point x bar at which the moment arm, also known as the fulcrum, could be relocated to obtain equilibrium. And just to make this all simple, in case this makes no sense, um, basically the idea is you have some object. You know, we're going to do it in two-dimensional space because 3D is not in the scope of this class. But let's say you had like a 2D plate, right? You have a plate, and you want to balance it on a fulcrum, or let's say on a pointy stick or a needle or something, right? Who cares? If you want to balance it on the plate, you need to find that center of mass. And when you find it, the plate will be perfectly balanced and it won't fall. That would be a state of equilibrium. So that point would be the x value would be represented by the location on the plate. The x part would be x bar. Okay. And they're saying in this paragraph here that you can move the fulcrum or the stick to find the equilibrium. And given the shape or in our case, we'll have functions that define the plate or whatever we're talking about. We can find the x bar and the y bar, which will be a coordinate, almost like an average that finds the equilibrium point. Okay, that's the goal of this section, finding that point, and it will require integrals and some understanding. Okay, but that's the goal. So moment and center of mass, one-dimensional system. All right, so for one-dimensional, this will be an easy one. Let me give you the rundown. So let the point masses m1, m2, all the way till mn be located at x1, x2, x3, all the way to xn, respectively. So number one, the origin I'm sorry. So the first part of this, the moment about the origin is m sub 0, which would be equal to the sum of the mass times uh, each individual point. So mass 1, mass 2, and x2, all the way to mn xn. Okay, number 2. The center of mass is x bar, which will be equal to m naught, which is the summation, right, of all those pieces, divided by m. Okay, so this m on the bottom, where m is the total mass of the system. I.e., that is to say that m is equal to m1 plus m2 plus m3 all the way to mn. All right, so a one-dimensional problem is what we're going to do first. Then we'll go to 2D. Okay. To find the center of mass of a linear system. In other words, in a one-dimensional problem. They're going to give you a chart like this, almost like a distribution. So you have 10 and negative 5, 15 and 0, 5 and 4, 10 and 7. So the first thing you got to do is get the total mass, right? So little m, it'll be the summations of all these guys here, which is about 40, right? 15, 5, 20, 10, 40, yeah. M0, we said, is each individual uh, mass times that x value, okay? So the idea, I guess, picture this. So here we got 0, 4, no, 7's over here somewhere. Negative 5's over here, right? These are all the x values. So we want to find a specific point that will balance all this, because each of these points has a different mass assigned to it. So if I were to balance this one-dimensional thing on my pen here, like where is that specific point, right? That's what we got to calculate. That's what x bar represents. So 10 times negative 5 plus 15 times 5 plus 5 times 4 plus, oops, that should be 0 plus 10 times 7. So that would be a total of what? This is 0, this is negative 50. 70 and negative 50 is 20 plus 20. Yeah, this is 40. So in this case, the formula says that x bar is equal to, right, m naught over m. In this case, they're the same. So 1. So 1, that's somewhere around here, right? So this little spot here is the center of mass for this linear system. Does that make sense? I think what the goal is here. All right. Let's move on to two-dimensional. So one-dimensional is not too bad, right? You just got to find that center x point. Two-dimensional, you have to find an x and a y. So moments and center of mass is a two-dimensional system. All right. But first, let's define stuff. Let the point masses, right, these are all masses at a single point, m1, m2, mn, be located yeah, this should fit here. Located at x1, y1, x2, y2, xn, yn, respectively. So each of these mass points, or point masses, will be located at their respective m1, x1, y1, m2, x2, y2, mn at xn, yn. Okay, so those are all the locations of these points of mass. Okay, so the first thing, the moment about the y-axis is capital Y, my, equal to m1, x1 plus m2, x2 all the way till mn, xn. Number 2, the moment about the x-axis is mx equal to m1y1 plus no, yeah, it's fine. Sorry, this threw me for a second. M2 y2 all the way till mnyn. Okay, number 3. The center of mass will be x bar, y bar, and x bar is defined as the capital My over the total mass of the object. Y bar will be equal to mx over total mass. Okay, in this case you forgot, m is m1 plus m2 plus mn all the way. Okay. All right, so let's do another example. Let me find one. Okay. To find the center of mass of the system of point masses located according to the chart below. All right, so similar to the last one, you got the masses here and their specific locations. X, I, Y, I. So 6 is at 3, -2. I feel like it's a little zoomed out. I can't tell. 3 is at 0, 0. 9 is at 4, 2. Okay. The first thing we need is a total mass. Let's just add it up. 6 plus 3 plus 2 plus 9. What is that? 15, 20? Yeah. So now we got to find, so similar like we did the last question, you got to find the my and the mx. So we did mx last time. So my will just take the y values and multiply it by the masses. Wait, actually, hold on. I'm dyslexic, so my is defined m1 with the x's, mx is defined with the y's. So when I'm doing the mass of the y, sorry, the moment, I'm going to multiply the mass times the x value. The mass times its respective x. Yeah, there we go. I always get that mixed up in my head. Mx, well, Same deal, same masses, but now you choose the y values. So that would be negative 12, 6, and 18, right? This guy will be, I don't know, what's that going to be? 44? 12, yeah. Yes. Okay. Okay, now that we have that, we just follow the formula, right? Center of mass for the x value, we said is the my, the moment about the y-axis over the total mass. The y value will be, the y bar will be the moment about the x-axis over total mass. So that will be 44 over 20. And um, 12 over 20. That's what, 3/5, 11/5. So the center of mass is at the location 11/5, comma 3/5. Are there any questions about example 2? Okay. All right. Well, now let's do, instead of having a chart, we're going to have a function. So the function is going to create a, so kind of like when we did 7.1, do you remember how we had that, um, the area between two curves? It'd be like a bounded section or bounded region, I believe the book called it. So you're going to create that bounded region still, like before, but you're going to find what is the center of mass, assuming that region has uniform density. Right? Because if it's not uniform, then the question becomes much more complicated. But kind of like those physics questions, right? When they tell you in a vacuum, in a perfect world, just to make the problem a little more simple. Otherwise, it gets tough. Because reality is difficult. Okay. Let me give you the rundown first before we start. So moments and center of mass. The book calls this a planar lamina. Of a planar lamina. All right, so let's explain what the hell that means. A planar lamina is a thin, flat plate of material of constant density, which we'll call P. Maybe it's rho, I don't remember. Let F and G be continuous functions such that f of x is greater than g of x on a to b, and consider the planar lamina of uniform density P bounded by the graphs y equal f of x. Call this one, I don't know. Doesn't matter, I guess. Y equal, oh, I should use a different letter. U equals g of x. And x is between a and b. Okay. All right, so number one. The moments about the x-axis and y-axis are mx equal to p times the integral from a to b of f of x plus g of x over 2 times f of x minus g of x dx. My, the moment but the y-axis, is equal to the p density times the integral from a to b of x times f of x minus g of x dx. Number two, the center of mass of x bar y bar is given by x bar equal to the moment about the y over the total mass. Y bar is the moment about the x over the total mass, where total mass is given by this integral. Density times the integral of a to b times f of x minus g of x dx. So this is the mass of the lamina right here. All right. So let's do one more example and then we can call it a night or see if you have homework questions. Probably not going to have enough space here. Example 3. find the center of mass of meaning x bar y bar, right? For the lamina of uniform density P bounded by the graphs of y equal to square root of x plus 2 and y equal to 1/5 x plus 2. All right. So we have two functions. So maybe we should graph this first, see what the heck it looks like, right? Okay. Yeah, I'll do Desmos. All right, so we got y equal to square root x plus 2 and y equal to 1/5 x plus 2. All right. So most likely they want this bounded region here. See what I mean? From here to here. So I'm going to integrate from 0 to 25 to find the total mass of this object. Okay. So we need to find that point. Like if I were to cut this out of a piece of paper, right? Let's pretend it was a solid um, piece of plastic. And I wanted to find the single point that it will balance on, like on a needle or something. That is what we're looking for, the x bar, y bar. Okay. So in order to do so, we're going to need the total mass. Okay. So it's going to be, so the first thing we do is find the total mass, which is equal to P times the integral 0 to 25 of the top function minus the bottom function. So find this integral. That'll give us some number times P. Let's go ahead and do it. P times something. Integral root x, that would be 2/3 x to the 3/2 plus 2x minus 1/10 x squared plus 2x from 0 to 25, right? That's what we saw from the graph. So, oops, that should be minus. These would cancel, right? So, plug it in, see what it is. That will be P times 250 over 3 minus 625 over 10. So at this point, I'll just use a calculator. Who cares? 125 over 6 P. That's what our mass is. So now we got to find the mx and my. And you're going to see the p's are going to cancel when we start finding the m bar, or sorry, x bar, y bar. But we got the total mass, which is good. So now mx will be equal to, remember the formula said is going to be p times the integral from 0 to 25 of f minus g, right? It was on top. Yeah, it was. Times, well, let me check if it was times or plus. Plus. Oh, forgot this one piece. Times f minus g, I believe. Yeah. Times f minus g, which will be square root x minus 1/5 x dx. Okay, so at this point we just do the algebra and then do the integral, right? This will be, yeah, let's pull out the 2 over here, distribute, we can add these guys here. Trying to see if there's an easy way out of this, but I don't think so.
In that second bracket, is that the square root of x minus 1/5?
Yeah, 1/5 right there. All right, so this one will be, let's make it a little prettier. After you multiply all that garbage, you'll end up with this. I'm going to skip that step because I believe you guys know how to multiply variables at this point. Yeah, yeah. Yeah, that's right. That's a 4. 1 over 25 and 1/5. So integrate these guys, and you'll get p over 2 times 1/10 x squared minus 1 over 75 x cubed plus 4/3 x. Actually, sorry, that's not true. It'd be 4 times that. Be 8/3 x to the 3/2 from 0 to 25. once we plug in our number, that should be, using our calculator, it's about 375p over 4. So that would be mx. So now you can find an x bar, right? Because x bar is equal to, actually, no, that's not true. Let me see, because x bar is defined to be my. So I could find y bar right now. So y bar is equal to mx over m, which is equal to 375p over 4 over 125 over 6p. So you see how the p's are going to cancel, right? So these p's will be gone. You'll be left with 375 over 4 times 125 over 6. That should be 9 over 2 for y bar. Okay, so we got y bar. Now we need to get x bar. So we're gonna have to do the integral formula for my, the moment on the y-axis. Okay, so we just did mx, which allowed us to find y bar, and the m, the mass integral, will be used for both parts. Okay. All right. Yep. Okay. So my, the formula says is going to be the integral of times p, right? 0 to 25, same thing, of x times f minus g. So that would be, where the hell is f? Wrote it down somewhere. Yeah. Square root of x plus 2. Put some brackets here. Minus 1/5 x plus 2. Yeah. So we'll just integrate. This integral is not as bad as the last one, so that's good. So this will be x times the square root of x minus 1/5 x, because those 2's will cancel like last time. Okay, so multiply that x in there. So it'll be x to the 3/2 minus 1/5 x squared dx. That integral will be, add 1, that'll be 2/5 x to the 5/2 minus 1 over 15x cubed from 0 to 25. So that will be approximately something. That's fine, we'll do it. It'll be 1250 minus 3125 over 3 minus 0. So that'll be 625 over 3p. So now we can find x bar. X bar is equal to my over m, the mass and the moment. So that will be the my we just found, 625 p over 3, divided by the m, which will be, I forgot what it was. What was it? Oh, yeah. So 125 p over 6. So we get p's again cancel, leaving us with 625 over 3 times 6 over 125, which will become 10. So center of mass, x bar, y bar, is equal to 10 and 9 something, 9 fifths. 9, was it fifths? 9 halves, sorry. All right. So the integrals aren't too crazy. It's just a little messy. I think it's time consuming because we only did 3 questions and it took like an hour. But anyway, you guys have any questions on 7.6 or 7.5? You guys have any questions on the earlier homeworks? 7.4 or 3, etc. 7.2, 7.1. Right, if you have no questions, you're welcome to head out. If you want to stay, we can do a problem. Garrett, what's your question? Okay, so basically you're saying find the arc length of y equal ln sine from pi over 4 to 3 pi over 4, right? All right. And the formula for arc length is equal to the integral from a to b. Was it square root of 1 plus the derivative? Is that what it was? I forgot already. Let me check. Yeah, derivative squared. All right, so we need the derivative first. So y prime, right? Oh, be equal to 1 over sine x times times cosine. So it's equal to cotangent x, right? Or cosine x over sine x. We'll see which one is more helpful. So the integral from pi over 4 to 3 pi over 4 with the square root of 1 plus cotangent squared x. Yeah, that looks like the way to go because this is an identity. What is 1 plus cotangent squared? Yeah. Hold on a second. Just trying to share a screen with you, but it's not working. Here it is. Yeah, it'll be cosecant squared. So yeah, our identities are going to be useful here. So whenever you see like trig functions on arc length, you should assume or hope for a cancellation of the square root, because this is equal to cosecant squared x, because 1 plus cotangent is equal to cosecant squared. So now that's gone, right? Yeah, adjust the paper. That would be cosecant x dx. So what is the integral of cosecant? Let's see, I think it's negative. I think it's negative ln or something like that. Let me double check. I think it's negative ln cosecant plus cotangent, but hold on. Yeah, that's right. That was right. Sorry, I was double checking. Negative ln of cosecant x plus cotangent x from pi over 4 to 3 pi over 4. So that would be equal to, put it over here because I need space. Negative ln of cosecant of 3 pi over 4 plus cotangent of 3 pi over 4. Minus minus will be plus ln of cosecant of pi over 4 plus cotangent of pi over 4. Okay. So what is cosecant of pi over 4? And there should be 1 over sine. 3 pi over 4 would be nothing. It was 4, right? Not 2. Would be 3 pi over 4 would be 2 over root 2 plus, actually minus 1 plus cosecant of pi over 2 pi over 4. That would be 2 over root 2 plus 1. You got 4? Oh, sorry, saying pi 4. Yeah, this one, I don't think it's going to get much prettier. Then you could combine them technically into one logarithm and say, well, this is 2 over root 2 plus 1 over 2 over root 2 minus 1. You could also rationalize this and combine them and reduce the fraction. So you could do some algebra here and do ln of 2 over root 2 over 2 plus 1 over 2 root 2 over 2 minus 1. Those 2's are gone. So end up with ln of square root 2 plus 1 over square root 2 minus 1. That's as far as we can go. Well, that's not true. You could multiply by conjugate, but I think at this point I'm just, messing with it. It's just algebra at this point. But anyway, does that answer your question, Garrett? Okay. So find arc length of y equal to e to the x plus e to the negative x over 2, right? From 0 to 2. See, the derivative would be ex minus e negative x over 2. The arc length would be the integral from 0 to 2 of the square root of 1 plus this nonsense squared. Okay. So squaring this will give us what? Do it over here somewhere. That would be 4 on the bottom. This would be e2x ex times ex would be 0. So minus 2 plus e negative 2x. Interesting. Okay. Not very pretty, but there it is. Oh. Yeah. Yeah. So you got 1 plus e2x minus 2 plus e negative 2x over 4. Let's get the common denominator. That usually helps. That will be 4 plus e2x minus 2 plus e negative 2x over 4. Oh, okay, I think I see it now. So this would be e2x plus 2 plus e negative 2x over 4. Notice how this is very similar to this one, right? It's just a minus. So we're going to factor this back into one term, or one binomial, squared. This will just simply be ex actually, plus e negative x over 2 squared, which will then cancel the root and allow for an easy integral. Oh, the -2, talking about this one here? When you FOIL the top part, you're going to end up with a -2. So multiply all this top part out, and you'll see where these three come from. So here I went backwards. I said, well, I have the same three terms, so I know if I factor it, I should go back to here. There's something similar, right? So then here we just integrate and we get ex minus e negative x over 2 from 0 to 2, which will be some number. I don't know if I have space there. I'll do it over here. e2 minus e negative 2 over 2 minus this. Which becomes simply, actually it should be like that. This is 1 minus 1, so that's gone. So all we have left is this.